Welcome to this explainer. Look, today we're absolutely tearing down the illusion that caching is a simple fix. You see, literally anyone can throw Redis at a slow database and feel like an absolute hero when response times instantly drop, right? But actually, that's exactly where the junior mindset stops. Senior engineers, they treat Redis as a highly complex, volatile architectural layer where every single decision you make involves critical trade-offs. We're talking consistency, availability, and failure recovery. If you're looking to make that jump from a mid-level developer to a true senior, you have to understand the hidden physics of distributed systems. So let's get right into it. There is this massive, fundamental psychological shift in how top-tier engineers actually approach a production failure. When an outage hits, the contrast is stark. The junior approach is almost entirely reactive. You know the drill. They check the logs, maybe restart a failing pod, cross their fingers, and usually just blame the code. But the senior approach? It's systemic. Seniors completely ignore that immediate noise. Instead, they hunt for what we call the decision tree signal. That's the core indicator of a state or consensus failure. They fix the deep architectural flaws that even allowed the failure to exist in the first place. They aren't just putting a band-aid on symptoms, they're curing the disease. Okay, let's dive into this, because there's a really famous saying in distributed systems. Redis is fast and Redis is reliable, but it will faithfully amplify poor design decisions. Redis is not some magic bullet. If your underlying data architecture is fundamentally flawed, Redis is just going to help your system fail faster. Most of the time, Redis-related issues in production have incredibly little to do with Redis itself. They usually start from picking the wrong caching pattern, which inevitably leads to stale data, double writes, and that dreaded silent data corruption. Section 1. Choosing the right pattern. Senior engineers don't just memorize Redis commands. They carefully select caching patterns based on who actually owns data consistency. And this brilliantly illustrates exactly what we mean. There's no perfect pattern out there. You are always trading something away. Think of it like a giant puzzle. Cache aside gives you awesome low read latency, but you're stuck with eventual consistency. Write through? Great, you get strong consistency, but it absolutely punishes your write latency. And then there's right behind, giving you ultra-high throughput but sacrificing consistency and bringing in the real risk of data loss. Ultimately, the pattern you pick decides exactly who takes the hit when failures inevitably happen. Let's break down cache aside, or lazy loading. Honestly, this is the pattern that should be your default like 90% of the time. Here's the flow. The application checks Redis first. If it misses, it hits the primary database, populates the cache with a strict time to live, and then returns the data. So why do seniors absolutely love this? Simple, because Redis is never ever the absolute source of truth. Your database is. If Redis goes completely offline, your app still works. It just temporarily slows down. It's incredibly safe, and it completely isolates your system from a catastrophic app-killing failure. But what if you absolutely cannot afford stale data? Say, for financial ledgers. That's where write-through steps up. Every single write goes to both Redis and the database synchronously. It's super safe, but yeah, it doubles your write latency. On the totally opposite side, we have write behind. Here you write only to the cache and then asynchronously flush it to the database later on. It is unbelievably fast, perfect for massive telemetry streams or click tracking. But here's the catch. If that cache node crashes before the database syncs, that data is gone forever. Seniors only use write behind when they are perfectly fine with data spontaneously vanishing into thin air. Section 2, the consistency and latency trap. This brings us to a pretty harsh reality about the fundamental physics of distributed systems. You've probably heard of the CAP theorem, right? Well, seniors actually designed by the Passel-Say theorem. It basically says, if a network partition happens, you have to choose between availability or consistency. But here is the real kicker, the else part. Even when your system is running perfectly smoothly with absolutely zero network failures, you still have to trade latency for consistency. You simply cannot have lightning-fast reads and perfectly consistent data at the exact same time. No way. You literally have to pick one to optimize and one to sacrifice. And when we do decide to optimize for latency, we have to make sure we're looking at the right numbers. Junior developers almost always look at average latency. Senior developers, they completely ignore the average. Instead, they look at tail latency, the P95, P99, and P99.9 percentiles. Why? Because distributed systems multiply variance. Think about it. Your average response time might look like a blazing fast 50 milliseconds. But if your P99 is sitting at 3 seconds because of a cold cache or a garbage collection pause, that means 1 out of every 100 users is experiencing a completely broken, stalling app. Averages lie. Tail latency is your actual, true user experience. Let's move to Section 3 and see how this builds into real-world production cache examples. Theory is cool and all, but how do massive engineering orgs handle this under extreme load? $640 billion. Just wrap your head around that. That's the staggering volume of financial transactions Stripe processes every single year. And sitting right smack in the middle of that highly critical infrastructure is a ridiculously optimized Redis caching architecture, built to do exactly one thing flawlessly: prevent duplicate charges. Stripe pulls this off using idempotency. In distributed systems, you know network retries are just a constant fact of life. So, to prevent charging someone twice when their Wi-Fi blinks out, Stripe forces clients to send a unique UUID header. Stripe immediately checks a Redis distributed cache for that exact key. If it's already in there, boom, it returns the cached response without processing the payment a second time. They use a 24-hour TTL, and brilliantly, they actually hash the request parameters. This guarantees a client isn't accidentally reusing the same key for a totally different transaction. It's incredibly smart. Now, let's talk about Uber's scale. When you tap a button to request a ride, that single action cascades into 30,000 remote procedure calls across roughly 500 different microservices. With that deep level of interconnection, a tiny cache miss or just a 10-millisecond delay in some random downstream service can multiply and cascade into a complete system meltdown. At Uber's scale, aggressively tuning tail latency and orchestrating memory aren't just best practices, they're absolutely mandatory just to get the system to boot up. And you really can't deny the sheer power of doing this in memory. Take Relevance AI, for instance. They managed to drop their vector search latency from 2 full seconds all the way down to just 10 milliseconds. How? Simply by bringing the vector embeddings directly into Redis using its native similarity search. It's a massive 99% speed increase, and it just proves that consolidating your data layer into a unified in-memory engine can fundamentally rewrite the rules of your application's performance. Section 4. Surviving failures and outages. Look, building a fast system is honestly the easy part. Building a system that degrades gracefully when everything is on fire, that is the true test of a senior developer. Let me introduce you to the senior engineer's actual worst nightmare, the cache stampede. Some call it the thundering herd. Imagine you've got a viral news article, super popular data. Its Redis TTL naturally expires. Suddenly, in that exact moment, 5,000 concurrent user requests realize the cache is empty. What happens? All 5,000 threads simultaneously pivot and hammer your primary database at the exact same millisecond to rebuild it. Your database instantly melts down and your pagers start screaming. This right here is exactly how a naive cache aside setup can accidentally take out your entire database cluster. So the crucial point is how you control what gets kicked out of your cache. You absolutely must explicitly configure your eviction policies to match your data. If your app has hotkeys that are accessed constantly, use LFU, least frequently used. But if your traffic is spiky and comes in temporal bursts, go with LRU, least recently used. And please always use explicit TTLs. If you just blindly let your cache fill up and rely on random eviction, you're basically leaving a ticking time bomb right in the middle of your architecture. And speaking of ticking time bombs, we have to talk about exploding lists. This is a notorious silent killer, especially in Java environments. It happens when you have static collections, runaway event listeners, or unbounded queues that just accumulate data forever. Think about it. It literally doesn't matter how well you tuned your database or your Redis cache. If your worker nodes have an unbounded queue ingesting tasks faster than it can process them, it will silently eat up all your heap memory and crash the entire application instance without warning. Section 5. The ultimate senior move. We've talked patterns, latency, and surviving failures. But I want to leave you with the ultimate engineering philosophy that really separates the mid-level folks from the true senior system architects. Now, what's really interesting here is how seniors handle risk. Junior devs will often just alter a column, deploy, and pray it works. Seniors, they use the 3-phase migration pattern. First, they expand, meaning they write to both the old and new database structures simultaneously. Next, they migrate, running background reconciliation scripts to ensure the new data perfectly matches the old data. And finally, they contract, safely deleting the old code in schema. This completely guarantees zero downtime and gives you an instant rollback path if things go south. And that contraction phase leads us to this absolute undeniable truth. Senior developers don't write better code, they just delete more of it. There's this huge deletion paradox in software engineering. A junior developer's contribution graph usually looks like mountain peaks of endless new features, but the senior's graph, it looks like a valley. Your actual value as a backend engineer becomes inversely proportional to the amount of code you write. Why? Because every single line of code is a liability. It adds cognitive load, it creates tangled dependencies, and it demands constant future maintenance. If you want to level up your career today, become a ruthless deleter of code. Start hunting down these targets right now. Consolidate those redundant code patterns. Delete those dusty internal analytics dashboards no one looks at. Rip out the feature flags that have been turned on for 2 years straight. And most importantly, delete premature optimizations for scale that literally doesn't exist yet. If you built some wild elaborate caching layer for a dataset that updates once a month and gets 10 hits a day, delete it. So here's my challenge to you this week. Audit your architecture. Look hard at your Redis usage and your databases. Stop asking, how can I add this new functionality? And start asking, how can I solve this by removing old problems? The absolute fastest way to ship features isn't by adding more stuff. It's by removing the barriers that are slowing you down. Remember, the best code is the code that simply doesn't exist. So, what can you delete instead? Thanks for joining me on this explainer. I'll see you next time.